Welcome to the Exponential Derivatives podcast. We're taking the derivatives here of other exponential functions besides e of x, and then we're also going to look at the natural log of x. So we'll learn that derivative as well. All right, so here we have a power rule and we have an exponential. All right, so our derivative here. Derivative of x to the 10th is just going to be 10x to the 9th. That one was pretty easy. And then, of course, the derivative of 10 to the x, right? We have an exact copy times the derivative of the natural log of the base times the derivative of the exponent. Oops, my x here is like floating down. He's an exponent. He's not 10 to the 10x, it's 10 to the x. And times natural log of 10, and then times the derivative of the exponent. Of course, the exponent is 1, so the exponent is x, and the derivative of x is 1. So we're basically done with this problem. Super easy. Our derivative here is 10x to the 9th plus, let's move natural log 10 in front, natural log 10, and then let's use parentheses, otherwise it's kind of unclear, 10 to the x. And there we go. And that's the end of that problem. And that's actually my last one, I think, with exponentials, before I move on to log functions. All right, so y equals log b of x is equivalent to x equals b to the y, right? Because this is our base, and this is the exponent, and this is the result. This is what you get when you raise to a power. All right, the domain for our log functions are 0 to infinity, right? Because when we raise bases to powers, we get positive numbers. However, exponents can be anything, so the range is all real numbers. Right? And then the exponential function, its domain is all real numbers because the x value for this is the exponential here. Right? So y equals b to the x. Right? The exponents can be anything, but the result's going to be positive numbers. They're inverse functions. Their graphs are symmetric with respect to the line y equals x. There are many different bases for a logarithmic function. Two special logarithmic functions are the common logarithm. So the common logarithm has a base 10, and generally we don't write the base in there. And then the natural log has base e, and we write natural log of x, or an ln x. All right, so some properties of natural log, and they're going to come up as we're working with the natural log. So the natural log or the log, doesn't even have to be natural log, it could be any log. But since we're only working with natural log, we'll just talk about natural log. So natural log of a product is equal to the sum of the logs. The log of a quotient is equal to the difference of the logs. Right? If we have something raised to a power, it can move in front as a coefficient. Natural log and e are inverses of one another, and so they cancel each other out. And then here, natural log of 1 is 0 because e to the 0 is 1. All right, so those will come up, particularly that product rule is going to come up, power rule maybe. All right, so let's take a look at, of course, we're going to derive the formula for the derivative of the natural log. All right, so first of all, we have y equals natural log to the x. We're going to exponentiate both sides. It's a common technique when you're working with natural log is sometimes we exponentiate them. All right, and it eliminates natural log. So e to the y is equal to e to the natural log of x. So if you have a natural log when you're solving, you want to get rid of it. If you exponentiate both sides, you'll get rid of it. All right, so now we have e to the y. And e and natural log cancel themselves out, so that's x. We're going to take the derivative of both sides. This would be a chain rule. On the left-hand side, we do have implicit differentiation because we have a y. We're going to learn more about that in the next lesson. All right, so I'm going to take the derivative here. So d dx, take the derivative of e to the y, and take the derivative of x. All right, so the derivative of e to the y, the derivative of e to the anything is e to that thing, right? And then we take the derivative of the y. All right, so this is going to be e to the y times the derivative of y, and I'm just going to put that right here, is dy dx, right? We write that all the time. just never really thought about y, right? dy dx all the time. All right, so this is dy dx, but I'm just going to use dy. All right, so actually, you know what? Let's do dy dx. dy dx. And so now we have over here equals, the derivative of x is just 1. All right, now we're going to solve for dy dx, which means we're going to divide both sides by e to the y. So we have dy dx, so the derivative is equal to 1 over e to the y, but that's just really not the most helpful formula we've ever seen. However, earlier on, we said that e to the y was e to the natural log of x. Remember, it's right up here in step 1. Look at that when we exponentiated. So if I see e to the y, I can make that e to the natural log of x. All right, so I've got dy dx equals 1 over e to the natural log of x. Well, e and natural log are inverses of one another, and they cancel, leaving dy dx is equal to 1 over x. And now we have derived that formula. It makes sense as opposed to just learning some formula because I say so. All right? So here is the derivation of the derivative formula for natural log of x. All right, now let's work with natural log of x a little bit. All right, so the derivative of exponential function, chain rule for exponential function. So the derivative of natural log of x is 1 over x, but sometimes we take the natural log of something that's not just an x. All right, so if it's a whole function, all right, then we're going to have to use a chain rule, and it's going to be 1 over the function times the derivative of the function. Right? So if it's just natural log of x, our derivative is 1 over x. If it's natural log of some function, it's going to be the derivative of that function over that function. Right? So let's see some problems like that. All right, so here we want to find the derivative of f of x equals natural log of 2x squared minus 1. All right, so we have a function here, f of x, that we're taking the natural log of. That's 2x squared minus 1. Its derivative is 4x. So that means that our derivative here for the whole function, I guess I shouldn't have used f, since I have f as my equation over here. Let's use g so it doesn't look confusing. All right, so g of x. Oh, and I forgot to say, by the way, take notes. You have those in your note template, some of them. Anyway, all right, so now the derivative for the whole function, because that was the derivative of the inside part, is going to be 1 over 2x squared minus 1 times 4x, or 4x, over 2x squared minus 1. And there we go. There's our derivative. That's simple. Let's continue on. We're going to do a few more problems. Actually, we're going to finish up natural log. I'm going to stop before I get to logs with other bases. So here we want to find the equation of the tangent line to the graph f of x equals 2x plus natural log of x at 1, 2. If we didn't know the y coordinate, we could just plug it in. So f of 1 equals 2 times 1 plus the natural log of 1. 2 times 1 is 2, natural log of 1 is 0, so that's just 2. All right, so we're going to find the derivative first of all. All right, so that's going to be f prime of x is equal to, so the derivative of 2x is 2. And the derivative of the natural log of x is 1 over x, so not really difficult derivative there. We're going to find the slope, right? And so we plug into the derivative to find the slope. So we have f prime of 1 is equal to, 2 plus 1 over 1. All that work to write takes so long, and I put an x instead of a 1. Come on. There we go. So plus 1 over 1, which is going to give us 3. All right, so now the equation in point slope form, then we'll simplify. So we have y minus 2 equals 3 times x minus 1, which is y minus 2 equals 3x minus 3, and add 2 to both sides. Y equals 3x minus 1. And there we go. All right, so that's simple to find the equation of our tangent line. It's also acceptable to leave it in point slope, but here I put it in point slope and slope intercept form. All right, let's do some more problems. I think working with natural log is pretty nice and easy. So here I'm going to show you two ways to solve this problem. We're going to find the derivative if f of x equals natural log of 6. So remember we went over properties at the start of this lesson, that if we have the log of a product, that is the same as the sum of the log. So natural log of 6x equals natural log of 6 plus the natural log of x. Let's solve this two different ways. All right. So here I'm going to use our first rule. I'm just going to take the derivative, right? And remember the derivative for the natural log of x, when we've got something other than just an x, is going to be f prime of x over f of x. All right, so I'll call it g of x. So g of x here is 6x. Right? That's our function. That's our inside function. Its derivative would be 6. So the derivative for the natural log function would be, it'd be 6, right, over 6x. Well, that reduces to just 1 over x. Let's see what happens if I use the product rule for logs here. So the log of a product is the same as the sum of the logs. All right, so we've broken it apart, and now what if we took the derivative? So dy dx equals, natural log of 6 is a constant. And we know that the derivative of a constant is 0. So this would just be 0 plus net 1 over x, or 1 over x. Look at that. We got the same thing either way. And this one was pretty easy no matter which way we did it. But sometimes it's helpful to use properties of logs to simplify first and then take the derivative. Okay, so just a little thought there. All right, here's our next one. All right, we want to find the derivative of f of x equals x ln x. So we do have a product rule. Remember the derivative of a product rule. So if we have a product, its derivative is the first times the derivative of the second plus the second times the derivative of the first. Right? All right, so here our u is x and our v is ln x. The derivative of x is 1, and the derivative, I have to work on making my u's and v's not look identical. Here with this du, there, it looks a little roundier. All right, and then dv is going to be 1 over x. All right, so let's get our derivative here. All right, so we have f prime of x is equal to the first, which is x, times the derivative of the second, which is 1 over x. That's a horrible looking 1 over x. There we go. If it's coming in. Plus the second times the derivative of the first. All right, so that's going to give us, well, they're going to cancel each other out, so that's just going to be 1. So we have f prime of x equals 1 plus the natural log of x. All right, so there's our derivative. And that's all we needed to do. So that was pretty easy. We want to find the derivative, and I actually still have this up here, so that's okay. We want to find the derivative of f of x equals natural log of x squared plus 1. This would be a chain rule. Right? So our inside function here, g of x, is x squared plus 1. Its derivative is 2x. So then the derivative of natural log of x squared plus 1 is just going to be 2x over x squared plus 1. Easy cheesy lemon squeezy, huh? And this is where I'm going to stop. All right, so we've looked at the first three. Right, we've the derivative of an exponential function. Right, so if it's e to the x, and we have something other than x, so e to the f of x, where f of x is a function. Remember, it's going to be that the derivative is going to be an exact copy times the derivative of the exponent. If it's not e, but it's some other base, then it's going to be the exact same thing. It's going to be an exact copy times the derivative of the exponent, but then times natural log of the base, because it's not e. And now we've also learned that the natural log of f of x is equal to 1 over f of x times f prime of x. Right? So in other words, we have to take the derivative of the stuff we're taking a natural log of over the function itself. Right? And then in the next lesson, we're going to look at logs other than base e, other than natural log. All right, so this is the end of this podcast. Thanks for watching. Bye.